The fin to limb transition by Holly Brown, Katie Duggan and Maisie Parkin. The earliest known tetrapods lived approximately 375 million years ago in the Devonian period, and their closest living relatives today are lungfish and coelacanths. The transition from sea to land would have required many character alterations, including the fin to limb transition. Modern tetrapods have a one-bone, two-bone, little bones digit pattern. At first glance, this does not appear to correspond to fish fin structure, which includes lots of bones and fin rays. However, here we will demonstrate how to bridge the gap between the tetrapods and lobe-finned fish using intermediate fossils and studying underlying evolutionary development mechanisms.
The first tetrapod ancestor we are interested in is the Euthenopteron. It was fully aquatic and used its pectoral fins for swimming, but also was able to prop itself up at the bottom of lakes. The next species, Panderichthys, dwelled in shallow tidal flats or estuaries and is the most crownward stem tetrapod with paired fins. Tiktaalik is the most crownward positioned taxon before the origin of digits. It may have been able to support most of its weight with its fins and had a kind of palm that could lie flush against bottoms of rivers and streams, perhaps even using these for short trips out of the water across shallows and mudflats. Acanthostega can be described as an aquatic tetrapod. Although it has lungs, its skeleton would not have supported itself out of the water. Ichthyostega lived in shallow water and is the earliest known tetrapod to show adaptations for non-swimming movement. It may have dug nests on land and hunted in the water, likely moving like a seal. Finally, Tulopteron was primarily air-breathing and can be described as a eutetrapod.
Here we are modelling the changes in bone structure of the forelimb over evolutionary time to result in the humerus, radius, ulna and digits in modern tetrapods. These bones can be grouped into the stylopod, pseudopod and orthopod. This is Euthenopteron's pectoral fin bone structure. The fin web has decreased in size from that of its fishy ancestors, and the endoskeleton includes fewer segments proximo-distally relative to its ancestors. This is the structure of a Panderichthys pectoral fin. It has a humerus which is uniquely like one of a tetrapod compared to those in other fins. Tiktaalik adaptations help prevent buckling during loading of weight onto fins, such as a fleshy base of the palm for support. Additionally, dorsal fins were several times larger than ventral rays, suggesting it had muscles extending on the underside of its fins. The top and bottom of fins were becoming asymmetric, allowing joints to bend in one direction, probably for use on land. Acanthostega has some key novelties such as the complete absence of dermal fin rays and the presence of 8 digits, likely due to incomplete expression of HOXD13, showing pentadactyly isn't a strength trait as previously thought. Processes on the humerus indicate development and elaboration of the musculature. Ichthyostega had 7 digits. Its elbow joint mobility seen from the ulnar articulation is comparable to that in modern tetrapods. It is relatively flexible and shows a pattern intermediate between more sprawling animals and those that have a more upright limb posture. Tulopteron possesses 6 digits. It has simple ossified wrists, lacking distal carpals, but the intermedium cross-articulates like those of more derived tetrapods. The hind limb is more conventionally limb-like than the forelimb, closer resembling crown-grouped tetrapods despite its 6 digits. We have now reached living tetrapods such as ourselves. The limbs of tetrapods can be determined by the absence of dermal skeleton and the presence of digits, parallel non-branching and segmented endoskeletal elements at the distal end of vertebrate paired pectoral and pelvic appendages.
By bridging the gap with intermediate fossils, scientists have been able to decipher experiments to understand some of the underlying genetic mechanisms of the fin-to-limb transition. There are differential changes that have allowed the development of limbs from fins, including changes in the apical ectodermal ridge (AER), factors such as the expression of sonic hedgehog, positioning along the 3 limb axes, and other mutations. The apical ectodermal ridge is at the tip of the limb bud and corresponds to a thickening of the ectoderm. In fish fins, this transitions into an apical fold, which gives rise to a fin paddle, whereas in tetrapods, the AER eventually undergoes apoptosis. Studies comparing HOX genes in modern tetrapods and fish have confirmed that fish have the genetic apparatus to drive HOX gene activity, which creates digits in tetrapods. Recently, AND1 and AND2 were found to be important genes in the loss of fins via the loss of rows of rigid fibers called echinotrichia that provide structural support and guide fin development. These are not present in tetrapods.
A combination of genetic experiments on living species along with the fossil record has enabled us to piece together this transition, and thank you for watching.